¿Tú ves esto?
No, yo soy presente, sí. Soy un ruido ahí de fondo.
Ya, es por esto, es que Willem necesita...
Vale, no pasa nada. Sí, yo también. Es que como el vídeo. Esto está apagado.
Lo que quería.
¿Cómo?
Me lleva justo aquí.
Ah, sí. Y pero el Darío no es para apagar, ¿no?
Ahora mismo está aquí y en rojo quiere decir que está. ¿Vale? Sí.
Vale. Bueno, hola, bienvenidos a una sesión nueva de Meetup. Es el primero que hacemos en 2008, así que bueno, esperamos que hayáis empezado bien el año y que lo sigamos mejorando y nos lo pasemos todos muy bien. Bueno, yo soy Victoria Gómez. ¿Cuánta gente de las que estáis aquí habéis venido ya con anterioridad a otro Meetup? Vale, bueno, entonces veo que hay algunas caras nuevas. Muy bien, porque os voy a poner, quiero que... O sea, vosotros pensad, ¿no? Los que sea la primera vez que venís, ¿qué habéis pensado según habéis entrado, ¿no?, por la puerta de IBM? O cuando visteis el Meetup, que digamos lo lleva, ¿no?, la gente de IBM, ¿qué es lo que habéis pensado? Y si es algo parecido a esto o no.
Wait for me, girl, wait for me. Wait for me, girl, wait for me. Wait for me, world, wait for me. Wait for me, world, wait for me. Wait for me. Let's keep on this song down. Don't take that long to come out. Wait for me, butterfly, wait for me. I'm only trying to set you free. Wait for me, problems, wait for me. I'm only human, so let me be. Let me be. Let's keep running, so go down. Don't chase that one to the ground. Let's keep running, so go down.
Bueno, pues en parte, ¿no? O sea, aparte de del vídeo, de lo que decía el vídeo, ¿no? Es por lo que estamos aquí hoy, ¿no? Por esta apuesta que hacemos y nuestra contribución a lo que es el mundo del open source y que ahora iremos viendo a lo largo de la introducción. ¿Cuántos de vosotros conocéis, ¿no?, esta faceta nuestra o es algo nuevo para vosotros? La agenda. Hoy tenemos varios invitados internacionales, digamos. Bueno, vamos a empezar en español, con mi introducción. Luego vamos a pasar con Raúl Marín, la persona de Hortonworks, que está aquí, Solutions Engineer de Hortonworks, que nos va a hablar de ese caso de uso real de IoT, utilizando, bueno, pues, lo que sería el Hortonworks Data Platform y Hortonworks Data Flow. Luego vamos a pasar a Willem Hendriks. Willem es uno de nuestros científicos de datos de Europa y bueno, yo siempre digo que es uno además de nuestros mejores aquí en conjunto con Nikolai Manchev, que es otro de nuestros data scientists. No, don't worry, I'm not saying you're going to talk, I'm just introducing you. Y luego, bueno, por último, para hacer un poquito de cierre, a lo mejor contaros también alguna cosa más, está Frank Kettelars, que digamos sería mi homónimo, es el responsable de la parte de preventas, de Technology Sales para Europa de IBM. Bueno, pues lo que os decía, ¿no? Estamos aquí por nuestra contribución a Open Source y de hecho, bueno, estos meetups, como habéis visto, los que habéis participado más veces y los que no, si habéis cotillado un poco, ¿no?, los pasados, veréis que nuestro foco principal y lo que nos gusta hablar es de tecnología open source. Contribuimos, ¿no? Desde, no es algo que sea nuevo, esto ya llevamos contribuyendo desde el año 1998, somos miembros fundadores, 1999 como miembros fundadores de Apache Software Foundation, y luego, bueno, pues tenemos algunas contribuciones, digamos, más relevantes o más especiales, como pueden ser en Cloud Foundry también somos el contribuidor número 1 y el número 2 en Spark. Aunque tenemos mucho foco en Spark, de hecho tenemos un centro en San Francisco, el Spark Technology Center, con ingenieros dedicados a contribuir a Spark, y de hecho en algunos de los proyectos somos contribuidores número 1, como por ejemplo en la parte de Machine Learning. Además, para un poco, digamos, reforzar aún más, ¿no?, nuestra apuesta en el mundo open source, desde el año pasado, desde junio, hemos hecho una alianza con Hortonworks, ¿no? Bueno, es, digamos, nuestra solución o nuestra distribución Hadoop, está basada, bueno, es Hortonworks, utilizamos la plataforma de Hortonworks. Además, tanto nosotros como ellos, las gráficas aquí que veis, la barra primera es IBM, la segunda es Hortonworks, esta es nuestra contribución a Apache Software Foundation, con lo que podéis ver que, bueno, que entre los dos somos uno de los jugadores estratégicos, digamos, en el mercado, o sea, en el mercado, no, en el área de open source, ¿no?, la comunidad. Esto no es, hay mucha gente que me dice, ¿y esto por qué, no? O sea, ¿por qué habéis tomado esa decisión? Bueno, yo siempre digo que estábamos ya saliendo, ¿no? Estábamos ahí, empezamos primero con lo que fue fundamos ODPI, que ODPI es el Open Data Platform Initiative, que lo que persigue precisamente, o sea, lo que queremos es una mayor adopción de Apache Hadoop por las empresas, y lo que perseguimos es la estandarización y la simplificación. Y nuestro objetivo último es la interoperabilidad de las plataformas, ¿no? O sea, esos son los objetivos de esta iniciativa, del ODPI. Con ello lo que pretendemos es que, bueno, pues un cliente desarrolle una aplicación sobre una plataforma de Hadoop, si lo hace sobre cualquiera de las que están adheridas a este grupo, a esta iniciativa, puede correr sobre otra de forma transparente, o sea, sin tener que hacer cambios. Y para un integrador significa que lo hace una vez, se certifica una vez y sabe que puede correr sobre cualquiera de las distribuciones de Hadoop de los miembros de la iniciativa. Con lo cual, lo que buscamos, digamos, es cada vez más, digamos, la apertura, ¿no?, y el contribuir o ayudar a esa adopción por parte empresarial de Apache Hadoop. Luego, bueno, pues hicimos además, antes, digamos, de llegar al punto de adoptar su plataforma de Hadoop, tuvimos también un partnership ya con el área de Power, que es, bueno, eso es nuestro área de hardware, ¿no? Ya alcanzamos ya un primer partnership con ellos, luego ya certificamos lo que es nuestro motor de SQL para hacer optimización de queries complejas sobre ellos, y ya el año pasado ya nos casamos, digamos. Y ahí ya pues directamente hemos adoptado su plataforma. Además, lo que buscamos con esto, digamos, como fin último, es pues llevarnos, o sea, no es quedarnos solamente en la parte de Big Data, sino es este partnership que tenemos, extrapolarlo y llevarlo a toda la parte de Data Science, ¿no? Es llevar Data Science a todos los sitios, ¿no? Escalarlo. Data Science Experience, que además es la herramienta esta, digamos, con la que, bueno, la plataforma sobre la que hacemos temas de Machine Learning y Deep Learning, es una plataforma abierta, o sea, está basada en Spark, utiliza Jupyter Notebooks y RStudio, o sea que, y si alguien está interesado lo podéis probar aquí en datascience.ibm.com. Os damos 2 ejemplares de Spark gratuitos en la nube y además es de uso ilimitado. Con lo cual, bueno, nos va a valer para hacer un proyecto de Deep Learning o de Machine Learning a nivel, digamos, empresarial, pero si vosotros os gusta cacharrear, os gusta generaros vuestros algoritmos y modelos y queréis, esta plataforma la tenéis disponible para vosotros de forma gratuita, está basada en open source, con lo cual que todo lo que hagáis, o sea, es que no va a haber nada que os limite ni nada, ¿de acuerdo? Bueno, y luego por otro lado, siguen hablando de más cosas que tenemos que a lo mejor no conocéis. Esto es lo que antiguamente se llamaba el bigdatauniversity.com. Son cursos online y gratuitos. Y aquí tenéis de todo lo que os podéis imaginar. Entiendo que estando aquí hoy estáis interesados en el área de Big Data y Data Science. Aquí podéis encontrar desde cursos de Spark, de Big Data, de Python, Hadoop, Scala, R, Machine Learning. Todo lo que podéis imaginar lo tenemos aquí. Y también es gratuito. Ahora le hemos cambiado el nombre y ahora se llama cognitiveclass.ai. ¿Vale? Y por último, siempre esto me gusta contarlo porque también tenemos programas para emprendedores. Y como en los meetups, bueno, pues no siempre venís los mismos, me gusta contarlo por si acaso hay alguno que no ha venido anteriormente y que viene hoy por primera vez. Si eres un emprendedor, tenemos también programas de ayuda. Damos, en función del tipo de, digamos, de soluciones que estéis creando, ¿no? Damos ayudas desde $1.000 al mes en nuestra tecnología en la nube hasta $10.000 al mes para aquellas que ya cualifican porque están ya más cercanos a temas de inteligencia artificial, cognitivos, etc. Si alguien está interesado, bueno, pues puede entrar en este link o si no, como luego vamos a estar tomándonos la pizza y las cervezas, podéis también acercar a mí y lo comentamos. Bueno, y yo ya no quiero entreteneros más porque sé que estáis deseando ver a Raúl y a Willem y además así cumplimos los tiempos que la última vez en diciembre nos fuimos un poco y alguno ya me regañasteis. Entonces vamos a intentar hoy ajustarnos un poquito más. Os dejo entonces con Raúl, empieza primero y luego Willem. Tú también ajustate, ¿eh?
Sí, sí. ¿Tengo media hora?
Sí. Bueno, no sé si decirte, tú tienes ahora que enchufar todo, ¿verdad?
Yo voy a utilizar el slide aquí.
Le digo a... you have everything in the computer?
It's already on the computer, yes. But
Le
Cambiamos.
digo si no.
Sí.
Bueno, ¿os importa que empecemos si no mejor con Willem, que tiene todo cargado en el ordenador? Willem es la persona del Data Scientist que va a hablar sobre Deep Learning. Y luego pasamos a Raúl, que como hay que tocar los cables, no vaya a ser que si no desconfigure algo. Sí, yes, you can go first.
Because my talk will be a little bit longer, maybe. So I have a loose end. So I prefer to be the
I can
second.
tell you, stop.
Okay,
Oh,
all right.
Okay, now, yes, I stop.
All right. Hello, everybody. My name is Willem. So my goal was to do a little introduction in deep learning, and I start from the bottom. My presentation is quite long, so who knows, we get till the end. The start will start with multiplication, and I think everybody will be still with me. At the end, we'll try to make a deep learning network drunk, because it performs better when it's drunk, strange enough. So that is the end. Who knows, we could get there. But this is what I'm going to tell. An intro in deep learning. What are they, what they can do, how to create them. My goal was to code a little bit together. All the code is on GitHub, so at the end I will tell you the URL. And like you said, the data science experience online, you can use that and do all the examples. I all checked them, they all were there. So it's a good way to start if you haven't yet. So this is what I'm going to do. But who already trained a neural network? Who already know what it is? Can I see some? Still a few. Oh, good. So for you, everything in the beginning you already know. Who doesn't know what deep learning is and wants to know? Oh, a little bit less. So we can maybe go a little bit faster and then see if we can get to the drunk part. So what are they? Sometimes people ask what is data science, machine learning and artificial intelligence, and I never really know how to give a good answer, but there's a guy, David Robinson, and he made it really simple. He says, you have to see data science, machine learning and artificial intelligence about what they produce. And he makes it very simple. Data science produces insights, machine learning produces predictions, and artificial intelligence produces actions. And he claims, he says, yeah, it's maybe a little bit oversimplified, but I like it because when I'm going to make a prediction, I'm busy with machine learning. And when I make a robot that actually do an action, we can call it AI, so I'm really comfortable with. And deep learning is part of the school of machine learning. So it's a technique that creates predictions. So when we talk about deep learning, it's part of the school of machine learning. And deep learning is actually what we used to call just neural networks. And I'm more comfortable with the term neural networks, but you could, any time I say neural networks, you can swap it to deep learning or the other way around. And there's also a slide where I do a little bit more explanation, but to make it simple, deep learning is applying neural networks. So starting with a multiplication. 4 times 2 is 8. That's really simple. A computer can do it. We can do it. And I'm going to write the multiplication with an arrow. So 4 times 2 is 8. And think of the arrow as a multiplication. And I can do another number with multiplication. 3 times 2 is 6. And now I have, on the left we call it inputs, on the right we have outputs. I have 2 numbers and I want to add them together. 8 plus 6. I'm going to write it down as a circle, and then we have just a way to notate a multiplication and an addition. Arrows are multiplications, circles are summation, additions, and this way we can write down a calculation, right? Nothing fancy happens. So I can do it multiple times. I can do it with more inputs. Again, the arrows is a multiplication. If you see a circle, all the inputs are summed to a number, and we can repeat this and repeat this. And what you see here is actually what we can already call a neural network. So doing this and vary certain things, more inputs, outputs, different designs, that is deep learning. That are neural networks. And of course, the one thing we can change is what happens after we added all the numbers. We can keep it as it is, then nothing really special happens. But we're in Madrid, and in Madrid the temperature is never below 0. We can say any number below 0, we just make it 0. So if the addition, let's say -2 and minus 1 is -3, then alright, no temperature below 0. We change the number to 0. So up function, very simple. And Thor, with his hammer, he can smack down big numbers to anything between 0 and 1. So if we have a big number, Thor comes and smacks it to a small number between 0 and 1. These are variations. And this one is called linear, this one is called ReLU, and this one, there's different flavors of making the number small, but the most used if you read about it, is the sigmoid. And then we already pretty much have a lot to start doing deep learning. So that is a neural network. And like I said, there are many different designs, and each has its strengths and weaknesses. So here you see a little image where people experiment, and I had a talk with Nikolai and we talked about different designs. I would say that every day people will test a new design. So they will see, they change the design, the numbers, more arrows. Sometimes people get creative and tries to make all kinds of new connections, see if the network gets better in doing something. And if they found out, hey, this is pretty useful by accident, they make it in a paper, and there comes a new paper. And if people use the paper and say, wow, it also works here and here and here, then it gets popular and it gets used. And that's a little bit what's happening right now. We're just trying things and see if it's useful. So that is my first part. We know what neural networks are. Does anybody wants to know what they can do? Everybody, right? Yes, good. So I had a few examples that I think are very funny. One of them is the input can be an image, and a neural network can actually fix images. This is an example of the deep image prior. It's not so easy to see, but here there's a low-res image becoming high-res. This one is much easier. So here there was things scratched away from the image, and then the network magically makes the image perfect again. And this one is also, I think, good to see. There's a lot of noise on the image, and then plop, a network suddenly makes the image perfect again. And the weird thing about this is that there was no training involved, so I don't know what really happened there. But another one, networks can draw. And if you haven't seen this one, it's really funny to do. It's an online game where you have to draw something. Randomly it chooses something, so I have to draw a cruise ship. So I'm gonna do my best to draw a cruise ship, and this is my first start. And then a neural network will finish the image based on a lot of inputs that they actually got by a game. So try it a few times, it's really fun. Neural networks can make music. So this is Chopin, or it's a neural network trying to mimic Chopin. I don't recognize Chopin in it, but it should be. And it was done by inputting music and let the network generate more music. So that's another example of what, oh, this is my favorite, then I will stop with the examples. They trained a neural network to tweet like Trump, and they called it Deep Trump. And this one is really, really good. So let's go through the last tweet that was generated by a network. Go Vive. So, well, it's incredible, right? Oh, this is the CSI Enhance, where an image is enhanced. This one is also pretty impressive. A network can create an image based on text, so you can say a cat with a red tail, and plop, suddenly an image will be created with a cat with a red tail. Alright, this one is also beautiful. Text to speech. So in here, the input is text.
It was the classic chair. There's still German, but not in on society, the fact that computer so.
It
It sounds English, but it's nothing. So in the commands on YouTube, somebody says, this must be if you listen to English speakers, but you don't know English. The network is not yet so well trained, but here's an example of the one that is fully trained and working.
Aspects of the sublime in English poetry and painting, 1770 to 1850.
So that one was pretty impressive, right? I tried to do it again.
Aspects of the sublime in English poetry and painting, 1770 to 1850.
That one is really like a human voice, right? Yeah, I would be fooled by that one.
What is it saying? Is she reading something?
It's a network. Input is text, and then the output is really speech, really like it's a human saying the text. Okay, so we're going good. We know what they can do. Now the last part, let's create some neural networks. Let's see how they are created. And so this one is the longest. This one is a little bit difficult. So I'm gonna go through some theory, and then once we have enough theory, we're gonna create our first network, and we're gonna do it in the data science experience, and then see how they are actually built. So if we have machine learning, like David said, it's trying to predict something. And we do that with labeled data. So let's say I have images of cats and dogs, and I want to make a prediction. Given an image, tell me if this is a cat or a dog. It's a real famous task for neural nets. And we want to know how well does my network perform. And we do that by splitting our data with a test and train set. So I have labeled observation, images with cats and dogs. I split it, and one part I use to create my model, to predict if it's a cat or a dog. And the test set that the model never saw can then be used to see, alright, tell me if this is a cat or a dog, and if the network is 95% correct, we have created a neural network that is capable of recognizing cats and dogs. And this is happening in machine learning a lot because we want to have an honest way to tell if our prediction is accurate, and this is the way we usually do it. There's small variations, but this is the idea. And a network comes from brain, from humans, where I'm not a biologist. I make a lot of mistakes because sometimes there's an expert in the room. So no, that's actually not how it works. But the basics is more or less there's a neuron and then there's a dendrites, and signals are going through your brain. And if the neuron is activated, the signal is going through the dendrite. That is how your brain is a biological neural network. And once people start experimenting by making it artificial, and then the artificial neural network came. So we already know what this image is, because every line there's a multiplication, and the first layer is the input. So there could be a pixel value here, or a number, anything. If it's audio, the audio has to be first transferred to numbers to make them sure they can be inputted. Then every arrow represents a multiplication with a number. Here they are, again, all the numbers are summated, and then maybe we apply a function, like the Madrid one, that we keep it, the number as it is, unless it's negative, and we make it 0. And we repeat it until we have an output. And in the output layers, again, it can be numbers. Oh, there's a question there. Oh, no, sorry. And who knows, this number represents the probability that the image is a cat, and this the probability that it's a dog. But if we want to have music, we maybe need more output, and if we want to output the image, we maybe need more output, so we can fire right there. So the input sometimes is called feature, a unit. Earlier I talked about the Madrid function and about the Thor that's smacking the numbers down between 0 and 1. Well, we call that an activation function. So if we create a neural network, we have to choose an activation function. And the multiplication is always with a weight. So if we do times 2, then we call 2 the weight of this specific signal. And if we create a neural network, we must come up with a design. We must choose an activation function, and then the task of the computer is to find all the weights such that the output is what we want. Maybe the probability that's the cat of a dog. So that is the task for training a neural network. And like I said, there are many activation functions: linear, sigmoid, ReLU, and let's go over how the input is actually is for, let's say, an image. If I have an image of 28 by 28 pixel values and it's black and white, then I have 784 values going. So you would see 784 green little dots, each representing a number, each representing the light value of each of these pixels. So a small image is already creating a lot of inputs. If you have color, the way you encode color usually is RGB, the red, green, blue, then you have to multiply times 3, so I have 3 times as more input numbers. Voice, text, video, we can all handle it, but we have to find a way to create into numbers first. And of course, if you have a model like trying to predict if a customer is doing fraud or not, the number might be his bank account, his age, and etc. And if you want to make the neural network better, sometimes you can combine the values, like doing a mean or differences or VAR, so people are experimenting there, trying if you can see if the network can be better. Here are a few activation functions, so the sigmoid and the hyperbolicus thymus, is the family of Thor. This is the ReLU, so that is the one, let's call it the Madrid one. That is how they look. And here we have a very, very, very easy neural network. This is an example of a snail. I was searching for what is the most easy neural network that from an animal. I thought maybe I can mimic a little insect. And I stumbled on the article that somebody studied snails
And he found out that a snail makes the decision to eat or not based on 2 neurons in his brain. And they did a research, the article is in the slides. So I thought, all right, so if I want to model a snail, all I need is, let's say, two units, and then I can mimic the signal of the snail if it will take the food or not. And the snail has 2 inputs. One of them is how hungry he is. So one brain cell is telling, okay, I'm hungry or not. Right now I'm about 0.5, so later I'm happy there's pizza. If I have the pizza, then my hungry feeling is 0. Then I don't have hunger anymore. And if my hungry is 1, then I really need food and I will stop and run to the pizza. And then the second signal in his brain is if he sees food nearby. So if the snail is walking and he is on a leaf of a little plant, then he is right on the food. So his food signal is 1. But if he sees the food far, far away, he knows it's in his reach, but it's difficult to reach, so it's maybe 0.2. And based on these 2 signals, the snail will try to take the food or not. So this is how we mimic it. We need to have, let's say this snail has hunger feeling 0, and the weight on this moment is 2. Then we have 0.5 times 2. We do this for all the numbers, and then we can calculate the signal for this unit. And we can repeat this until we get a number, and this number might represent the chance that it will go for the food. Right? So. And now we have to choose an activation function. And my question is here, does anybody know what type of activation function is most mimics our brain? What is closest to our brain? Which one? The Thor. You say none of them is like our brain?
Well, I would argue that the brain is predominantly uses spiking.
Spiking. All right.
It's not based on the magnitude of the output.
So there's a different way of thinking. So sometimes people tell me it's the sigmoid, and now it's more spiky. But at least this ReLU, this Madrid way of the weather, is never the answer. But that one turns out to be really good for computers. So computers prefer the Madrid. And maybe some say that the natural way is more sigmoid. So the most used activation function nowadays is the ReLU, the one that keeps the number unless it's negative, it will do it to 0. And the one that mimics our brain, well, that maybe there's then none that is like our brain. And then the question is, given this structure, let's say this is the design of my network, and I have chosen an activation function. How should I set the weights such that my output is just like my labeled data? That it's just like my experiment I did in my garden with a little snail? That is the way how then I need to train the neural network. Everybody still with me? Right, good. So I have data. I have a little snail in my garden. 10,000 times I checked if he went for the food or not. I have a little machine and I saved this data in a file. It's on the GitHub, so you can check it later. And we're going to use this data to see if we can take a simple design and train it. And training a neural network, you could actually translate it to find the best weights such that the input and the output of the neural network is just like my test set, just like my labeled data, such that if I take a part of my data and put it through the network, then the outputs of the network is just like the labels of my data. And how does the computer do this? This is a picture of a museum, I think it's in England. What they did here is they asked 20 famous, I think it's in America, but well, doesn't matter. They asked 20 famous mathematicians, what is the most beautiful formula that you can think of? And would you like to
write this formula on a piece of paper. And they did this to 20 mathematicians. And I studied math, so I thought, oh, that's nice. So I looked through them. I didn't understand half of them. But one I still remember, that is Newton's method. And that is a method to find let's say the minimum point of any function, so to find the best point. And the way it does it is using the derivative of a function. So let's say I have this function and I want to find where the function is reaches 0. And I'm at this point, then I need to make a step either to the left or the right to get closer to the 0 point. And what Newton found out is if you take the derivative at this point and takes it as the direction to find your next x, then slowly you will go to the 0 point of the function. That is what we found out. Very simple, but very effective. And this is actually the base of the technique for a neural network to find the best weights. We don't have, if we have one weight, it would look like the Newton's method for a function. But in general, there are maybe thousands of weights, so the derivative looks a little bit different. But each time it takes a small step into the direction of the derivative to find the best weights. And this is training the neural network. So data is fired through the network. The weights in the beginning might give really weird answer, but there's an input. The weights will do the same. There's a calculation, there's an output, and there's an error with what the network should predict and what it actually does. And then with help of the derivative, all the weights will be calibrated a little bit closer to the answer. And that is with the derivative, and this is what the optimizer is actually doing when you train a neural network. So you take the design, we have labeled data, it's fired through the network. The weights are totally wrong, they will give a lot of wrong outputs, but we can, with help of the derivative, each time we can get closer to the optimal weight such that the network gives the output that we want. So, little example. I have a data point. Let's say the hunger feeling is a half, and he sees food really close by 1. These are the current weights, so it just pushes, it's calculated through the network, and there's a signal, and the network outputs 6, but maybe I encoded 10 as 1.0, 10 as the true signal, so we have an error of 4, and then based on the derivative, all the weights are a little bit calibrated such that next time it would be closer to the true label 10. That is what's happening when you train a neural network. And when I was thinking about this, I thought, oh yeah, this is a little bit like I'm studying something new. Because, what do I remember? I was not a good student, so I had to repeat a lot. I see a lot of nodding, so this is recognizable, I hope. There's something about the right speed. If I have a book and I do all the pages, I have learned nothing because it went too fast. And if I go slowly, page by page, I might be learning, but then it may take me a year to finish the book. So there's something about the speed of learning. And then usually, as I'm progressing through the books, the chapters get a little bit more difficult, so it might go slower. You know, the introduction, oh yeah, all right, blah, 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 done. First topic, all right, and then chapter 5, 6, usually the difficult topics come, so then it goes a little bit slower. And sometimes you skip a few pages because those thick books maybe have tens of examples. All right, example 1 I understand, 2, 3, 4, 5. All right, let's skip a few pages. That is how I studied. I see a few people nodding, so everybody recognizes this. And all these things are actually happening in a neural network during the training phase. Repeat, we call it epochs. So if the epoch is 2, the network will see 2 times all the training data. The speed at which it's learning is the learning rate. If you do the learning rate too high, the network won't learn. If you do it too slow, it's really like turning the pages 1 each month. It will learn, but it will never do the job because you have to wait an eternity. Slower towards the end,
you can do a training, it's called decay, and skip a few pages, that's called momentum. So in the code example, we will play a little bit with all these things and we'll see if the snail gets smarter. So first about the learning rate, the right speed.
So Newton gave the direction at which we should change the weights. And let's take this one. This is a derivative, so from here we have to take one step in that direction. I can take this step just as it is, then my learning rate would be 1. But I could also do just half of it, then my learning rate would be 0.5. Or just a tiny percent of it, 0.01. And my learning rate is actually the way that the weights are calibrated at each time the data goes through the network. So you can understand if it's very, very slow, it will go through the point, but at a really slow pace. But you might also understand if it's too high, then maybe this one will get, let's say, if the learning rate would be 10, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it would be somewhere here, and instead of finding the right minimum point, it will just hop around the minimum point, and the network will never learn. So that is a thing we need to do. If we're going to train a neural network, we have to input a learning rate.
And here are some examples of images where you can see if the learning rate is good or not.
At each epoch, so at each repetition of all the data, we can actually see with the test set how well does it perform on the test set, because the test set it was not part of the training, so that's a good metric to see if it learns. So on the x-axis you see the repetition, the epochs, and the loss function is the lower the better the network learns. And here somebody gives some images that you will see if you plot the learning graph for a network. And if the learning rate is ideal, you have the red one. So it's really going better, and the error is really going nice and steady, almost to 0. If you do it too high, you will see this yellow image. So let's see if we can try to get this exact image by doing a ridiculous high learning rate. And blue line would be if you choose a number small that it's learning, but a little bit too small, because sometimes it takes days to train a network, and if it's too small, it will take you a month, and then the result is too late for the actual application. And this is also too high, but it's still learning, but at the end it's going a little bit too fast through the pages. You might understand chapter 1 to 3, but then, alright, there's some concept, it just goes too fast.
Any questions so far? So decay, that is slower towards the end, then the training will slowly make the learning rate a little bit slower. Let's say at each epoch, at each repetition, we can take 10% of the learning rate off, and then it will be a little bit slower at each epoch, and it's a trick to get through the last few difficult chapters of the book, and it's called decay. Momentum is a little bit the opposite, that was skipping a few pages. If you're a few times in the right direction,
well, let's take a few extra steps, and then we're learning a little bit faster. So if the network can have some sort of scanner to see are the weights being changed in the right direction multiple times, then let's take a few big steps to skip a few pages, and it can help, especially in the beginning of the training, to get the learning faster.
So these are 2 tricks to speed up the learning. Enough talk, let's do the demo. So we now all understand the concepts. We're gonna make this snail demo. So I have labeled data of a snail. It has a column hunger, it has a column sees food, and then based on these signals it will make a decision, eat or not eat, and then we're gonna try a network to predict this taking food behavior of a little snail. So what do we need to do? We need to decide the number of layers and units. We need to choose an activation function, and for each layer we need to choose the number of units, and then we need to train. All right. So this is a notebook where I actually actually made a few codes to create this neural network. I'm using Keras. That is a library that helps me to model my network to actual code. And it's a very easy library. If you start making your first networks, my suggestion would be to take a look at Keras and a few others. Oh yeah, sorry. Yeah. So the first thing I do is loading the data.
And let's go through the first one. He has a really, really small hunger feeling of 0.05. Let's say he's only hungry for 5%. But food is right below him because 0.99. So he's on the leaf, but he doesn't hungry. So what did the snail do? No, he just passed. He didn't eat. And the second one, he was 70% hungry and 80% in reach of food. And he thought, yeah, let's take a bite, and then he eats. And I have a few thousands of those samples. So what we're going to do, we're going to cut it in about half. One part is to train it, the other one to see how our network performs.
And that happens here.
So it's not actually a half. I took 80% for the training, the remaining 20% for the test. And the eats and not eats, I have to do a little bit manipulation of the data such that it's no longer a piece of text, eats, not to eat, but actually a number. 0 is not eat and 1 is eat. And the hunger and food values were already numbers, so I just don't need, I can leave them as they are.
And this is a little bit of data preparation, and that's just a annoying thing you need to do when you're going to train your neural network, because somebody's giving you data, and it might sometimes take you a few hours to actually have the data prepared. This is code that is needed to make those little graphs that you saw of the learning curves. So there are some plotting and creating of figures, not so excited. Here is the actual design of the network.
So this is the interesting piece of code. So I'm creating a model, and it's a sequential model. That means that the layers are passing their signals through to the next layer, and like a sequence to the next, to the next, to the next, and then we have an output. There are many different designs, and some designs they will have feedback loops, and that we call them recurrent neural networks, and there are a lot of different designs like the page you saw. So this is an easy design, and we add a little layer. We add a layer. Dense means that every of the previous input values is connected with the next one. We have 2. This number is the number of units we have. We have to choose the activation function, so I choose sigmoid here. So I could change it to ReLU if I want. That was the one, the Madrid weather one. And Keras wants to know the input dimension. That is, how many columns are there in the input? Well, we had a signal for hunger and a signal for food, so that is 2. Maybe more complex animals base their decision to eat on more features, and then this might be higher. So this part is the design, but the network doesn't do anything yet. It's just the design, it still needs to be trained. And therefore, we needed the derivative and an optimizer that with help of the derivative, it will calibrate all the weights. And that is the optimizer. LR, anybody can guess what this is? Learning rate, indeed. So this is a 0.005 learning rate. That means each time it will calibrate the weights with a certain
factor of the derivative, 0.005. Then there's decay, so the learning rate will slowly decrease with a little decay. So at the last few epochs, it is a little bit smaller than 0.005. Then the momentum, so this is a way that if the training is going a few times in the same direction, it will make a big step. This is a little thing that has to do with the momentum. You have different ways to pick the momentum, so this is a little bit a detail thing. That one is true, but it has to do with the momentum. So still, the network isn't trained. I just designed it, and I just gave him, this is the way to solve this design. This is the optimizer. And here, I will compile my network into I will, let's say, glue the optimizer to my model, and then it's ready to be trained. So this is an important step. Did I execute the cell? I think so, right? Yeah. All right. No, I didn't. Anybody familiar with Jupyter Notebooks? Yeah?
You are all okay, right?
Yeah.
All right, good, thank you. So, here the actual training happened, and what we see is I choose 10 epochs, so 10 repetitions. I gave him a validation set, so that was the 20% left to do the performance. And the callback, that was the plot losses, that is the few of the plot calls I made earlier, such that we see this nice graph live. And the error is going slowly, but this is not the perfect curve, because this is a signal for me, if we go back to the presentation, that it was a little bit too slow. So let's retrain it, but then with a higher learning rate. So it was 0.005. I'm going to change it to 5. It's not a good guess, but of course I want to see the effect if the learning rate is too high. This can actually go. It's doing weird stuff, really weird stuff. It's like it's on drugs. It's not learning anything, it's giving weird output. So this is indeed the effect if the learning rate is too high. So let's try 0.05. This going better, so this looks good. So we have to wait till it did 10 repetitions of all the data. And who knows, this might be an okay network. Maybe it's still a little bit too high, but I just leave it there. And you can grab this code and play with it. It's the most easy design probably there is. And we have a network. So on this stage, the design of the network is exactly the same, except the weights are now chosen such that it really mimics the SNIL. Given a signal for hunger and given a signal for seize the food, it will output a percentage that the SNIL is likely to go grab the food. And here I have a few cases to test. So let's say the hunger signal is 1, so it cannot be more hungry than 1. It's really, really hungry. And it's quite close to food with 10%. So the network predicts a 1, which is encoded as it's going for the food. Another test, it's 50-50 hungry, 55% hungry, but it's really close to the food with 90%, and in this case it goes for the food. And then the last case, it is on the leaf, but only 30% hungry, and the snail didn't eat the food. So we can, like this, we could make an application. So according to David, this definition, I'm producing predictions. So this would be machine learning. if I make an actual mechanical snails that's doing this, then I would be AI according to his definitions, because then I'm actually performing actions. Alright, so here's the news article. It's Dutch, but it says, snails will do complex decision with just 2 brain cells. So they define taking food as a complex decision. And then there's a little bit, I think it's something from Nature, where I don't know how they did it. Maybe they put him in a machine to see how the brain is actually going. Another question. So I told you that during the training phase, Keras, which is the library I use to help me to design the network, needs the derivative. But I didn't enter any derivative. So how does Keras know what the derivative is? And it could only be one of the 2 answers. One answer is it knows what the derivative is because all the functions I used, Keras has also the derivative. So the ReLU, the sigmoid, it's somewhere in the library, it has dot derivative of ReLU dot derivative. And based on the derivative and the chain rule, it can find the derivative of my loss function and everything, that is the way it will know what the derivative is. So that's answer 1. It knows what the derivative is because it's somewhere in the Keras library with the chain rule. The other is, well, the derivative is a way to measure the chains, and a computer can really easily do that. Just put in 2 values and see the chains, and we can estimate the derivative. That's option 2. I never knew, and I was asking myself, who thinks it's option 1? It's all in the library. So Nicola, you, a few more. 1, 2, 3, 4, 5, 6. Who thinks option 2? 1, 2, 3, 4, 5, 6, 7. Yes, it's the second one. So it is based on TensorFlow, and it's really good at approximating those derivatives really fast. And I was actually a little bit surprised by this, because when you go to a book or a course, one of the first exercises is to actually calculate the derivative and put it in the solver. But that's not how most libraries do it. According to somebody on a Stack Overflow, so I copied his answer and I believed him, because I couldn't actually find it. I couldn't find the derivative in the libraries. And given that you can also put your own functions in there, it's also a signal for me that it's very flexible and can do any derivative. So that's funny. It calculates the derivative itself.
So are you saying that the symbolically expressed neural network in TensorFlow doesn't lead to a computational graph, which TensorFlow goes through backwards to actually compute the derivatives?
That's a really good question. Let's talk about it with the pizza.
Because option 2 implies this.
Yeah, might be, yeah. So, but while I'm not really certain, but as I know from the Stack Overflow, I believe it's doing some computational trick. It's first, the data from the first epoch is maybe, there's always a difference between the previous, and I guess that's how the derivative is. But if anybody knows more than this, please raise your hand and tell, because there will be a discussion at the pizzas for sure. But fortunately, that's not the only problem. There are much more problems, because I'm now saying that the things we can do with neural networks, all the cool examples of audio generation. Am I still good on time?
Yes, it's I got it.
Okay, good, all right.
So, how much more do you have?
How much more do I have? Yes, in time?
Another 3 minutes?
3 minutes?
No, 15.
15, all right, yeah, perfect. Yeah, that's just what I need. The few problems or challenges with neural network is the first is the need for data. This little snail example I already generated thousands of data points because neural networks need a lot of data. Sometimes we have the luxury that we can generate the data. One of the examples is that you can find on the internet a neural network to detect the license plate number. And well, computer can really do it. We take a font, we generate some random numbers with the dashes in between and some letters, and we can generate a lot of license plates. But that's not always the case. So sometimes you have the luxury that you can generate data sometimes not. And funny enough, other networks can help to get more data sometimes. So there's a lot of it. Overfitting is the second one. The network can be so good, it can understand so much complex relations that it will find relations in the train set that are actually not exist. For instance, if you try to predict cat and a dog, and by coincidence it had found that the pixel on the upper right is always a little bit lighter when it's a cat and a little bit darker when it's a dog. Just one little pixel could be a little bit that has nothing to do with it. It's a cat or a dog. So then it's overfitting. It's seeing things that it shouldn't see. Design choice, that's also a topic for pizza. Given a problem, how should I design my network? What is the best way? So there's not really a answer yet, but we're really smart. We can try smart. We have good examples, but nobody says, oh, this is the best design for this problem and this is a good flow. But fortunately, we're really close by inspecting the learning rate, by copying others. We can find a good design. The fourth, computers are too slow. Let's take that one. And it has a reason, because under the hood it's all linear algebra. And maybe the matrix multiplication is not everybody is familiar, but don't you worry. It's just the way we call the type of calculations that's happening when you train a neural network. It's matrix multiplication.
And there's always a cost of calculation. And you can go to Wikipedia and find cost of calculations of matrix multiplication. And you will find it's of the order n to the power 3. And the n is the number of inputs. So, I took a few examples. The FAF icon of your browser, if you go to a website and you bookmark it, you see this little icon. That's about 28 by 28 pixels. Let's say the cost of that would be 78 computing costs for the cycles of CPU. If I want to do a more complex network with a larger input, icon size of your computer on your desktop, it might be 128 times 128, and then the cost increases to almost 2000. So from about 80 to 2000, but boom, suddenly the computational cost is almost exploding. So if we increase the image, the icon of the iPad is about 256 by 256 pixels. You see that it's close to 7,000. Well, you get the idea. This function is really exploding great, and you not often see neural networks that can process images of more than 2,000 times 2,000, because by this law of the cost of matrix multiplication, it's just really a difficult calculation for a computer.
But there's a few people that did a lot of work to make sure that computers get better at this type of calculations. And I want to take this opportunity to thank them, because they are gamers. Snacks, Grims, Existence, Guardian, Device, Forest, Olofmeister and Kenneth. So these are online gamers, and they do shooters. They in a 3D environment, they try to make a headshot and see the blood splashing on the screen. And they are willing to pay a lot of money for this, because the blood has to be of high resolution. So the industry tried to create graphical cards that can do this really well, the GPUs. And lucky enough for people that like deep learning, creating a 3D game engine is also linear algebra. So if you Google creating your own 3D game engine, the first thing you find is pages about linear algebra, because it's also matrix multiplications. So thanks to these gamers and many others that are willing to pay for a nice computer, computers have gotten really good at this matrix multiplication thanks to the GPU. And if Forrest is playing online World of Warcraft kind of things, the GPU doesn't really know if it's playing World of Warcraft or training neural network, because for him it's just matrix multiplications. So that's good. We have GPUs. And to make it even better, IBM is doing a co-creation with NVIDIA to make even more use of the GPU, because the Intel architecture is limiting the throughput of the data to the GPU. So the GPU has gotten so fast that we cannot get the data fast enough to the GPU. And then the guys from Power, from IBM and NVIDIA have tried to overcome this with a special kind of link connection to the GPU, which is the NV-link. And then, of course, we're really proud to show the numbers. It's really, really fast. I'm from Amsterdam, and we got this machine, and as soon as it was there, with some colleagues, I went to the room and tried to test it out, and this is my first result. This is my own computer, so some calculation was really, really slow. This is the amount of time. This was the fastest machine there was, a Power 8 20-core machine, and this was the NV-link. It's just fast. It's really, really fast. It's the fastest bus to the GPU in the Netherlands, I should say. Not necessarily the fastest GPU, but the fastest entrance to the GPU. So the highway is just times 4. So we solved this problem. What we didn't solve is overfitting. So I will go quickly through the overfitting problem, but I don't think we have time to do the actual coding, but it's all on GitHub, and then you can try it out yourself. Because overfitting it's too much focused on the details. So when I'm learning and I'm so hyper-focused that I'm even paying attention to the page number, I'm not learning anymore. I should relax a little bit, because then you learn better. And one way to relax is take a coffee. Well, for me, the opposite happens. Somebody has more ideas of how to relax? Drinking. Thank you. Who was it?
Having a nap.
Having a nap, but drinking was the good one. Thank you for the one that says drinking, because taking alcohol also relaxes. And I thought that alcohol kills neurons, but it's fake. It's a myth, according to this website. And if you read it, you will see it doesn't really kill brain cells, but it can damage the dendrites, which are the branch-like ends of the brain cells connecting and passing signals. So the dendrites are those arrows, right? They pass the signals, the notification. That is the dendrite in the artificial neural networks. So this page is telling alcohol kills the dendrite, kills the connections. And this alcohol idea, neural networks took it to make a too-stressed network relax a little bit to prevent overfitting, and it's called dropout. But I actually think it's feeding alcohol. So when I apply dropout, I just think of, I'm giving the network some drink, and it's actually really, really close to alcohol, because you have to tell him an alcohol percentage. They say a float between 0 and 1. So that just means what is the drink you're going to give? You're going to give a beer of 5%. You're going to give maybe a wine 15%, 12%, or more, a vodka, a whiskey. Anybody has an idea what's the favorite drink of a neural network? Whiskey? Sure. Yes. It likes strong alcohol. So if you want to apply overfitting dropout, you want to apply dropout to prevent overfitting, give him some whiskey, 0.4 or 0.5, strong alcohol, vodka, because that is what the networks will perform with. So in this demo, which I'm not doing now, there's an example where you can give the network alcohol, and then you will see that the learning rates will not overfit. All right, but you can go to the, I create a little bit.ly, there's the code example and this presentation, and well, you can do it as the exercise. So it's made for the data science experience. You can all load the examples right there, and there's many, many more things to talk about. Here's a few topics for the pizza, but I want to stop here and go to the next presentation. Oh, questions, of course.
Questions. Well, it's not a question, it's a correction.
Oh, correction.
Come over here. Just
yes.
I want to quickly show you, because then I hate being wrong. That's the source code of TensorFlow on GitHub. Yeah. And if you take a look here, they have the derivatives for all activation functions. So that's
Ah.
the sigmoid, 1 minus
So we
x
were
times x. That's the hyperbolic tangent here, 1 minus x squared.
Ah, so there
it's
is
all
a derivative.
inside. Yes,
It's all
they
inside.
don't approximate anything.
So
Don't always be
I'm doubting now between Stack Overflow and this. So
You want to look at the official documentation?
Yes,
I
yes,
also
yes.
Googled this as well.
We'll do something then. We will do some more research and we will see the next meetup who was right. We will invite them again in the next meetup.
A topic about derivative from how does TensorFlow? Yes, it's a nice topic for.
By the way, did everybody know what TensorFlow and Keras is? You all? Raise your hand so we know.
I don't know what's TensorFlow.
Oh, well,
Okay.
if you want to make a network, so let's say you have your design. This was our. Where's the? Yeah, this is our design. The computer has actually take this design and put it in application with some data, right? And it's quite a lot of code if you want to start from scratch. So ideally, we use a library that we just say, oh, I want to use this activation function, this many units, this many layers, and all the code will be made for us. And Keras is one of the many libraries that will help you to fastly create and train a neural network.
Yeah, okay, I'm from our programming language.
Ah.
We use neural net,
Yeah.
neural net for our programming, and what I don't know is what that mean really. TensorFlow. TensorFlow is a tool. Sorry, an open source tool.
Yes, it's an open source tool,
Okay.
and it's more general. The most used application is for neural nets, but it's a general way to do calculations, and you're really free. It has the derivative of activation functions, and one way to use it is to train neural nets. But
Where can I find TensorFlow? Is this on the cloud? Or?
Created by Google and then they made it open
Okay,
source.
yeah,
you can download the
Yeah,
tool.
or if
Okay.
you, for instance, if you go to this example, as he said, is in GitHub available to you. You can go, for instance, to the datascienceexperience.com, and there it's very easy to run the Keras and the TensorFlow. Do you have the?
yeah, it's right here.
It's just like calling the library,
Oh yes.
and then you use it.
So 1.5 has just arrived,
Okay.
and then all your examples for
Sorry my
1.4
ignorance.
doesn't work anymore. So that's
I've heard about it.
yeah.
Probably. I thought it was a kind of tool in the cloud or something, but I didn't really know that it was at your reach of your hand by using Google.
Yes, and the NVLink is supporting so TensorFlow has been optimized for the NVLink recompiled, I should say, so that general code of TensorFlow can make use of this fast NVLink of the power AI.
Okay, thank you for the.
So you
Sure.
can download it and install it in your computer, whatever, from that tensorflow.org, or if you go to the notebook, maybe we can show where you call it. Do you have the notebook?
Oh yes.
Based on Python?
Yes.
Yeah. That's the reason why I didn't know about it.
Yeah, it's
Yeah, okay.
not, on the other. I'm saying on DSX, but it's okay. So you see that?
Oh yes, sure. Yeah.
You call it?
Yeah, I know exactly what you mean now right now. Thank you.
Okay. Welcome. So you have this example available, and like I said, you can take it from GitHub and install it on your computer, or you can also access Data Science Experience, which is free and it's unlimited usage. You can do the snail neural network. You
Yeah.
may not be able to do a human-like network with huge input, right? Because it's only to Spark executors.
Yeah.
So, but you can. It's very easy. Log in and you have everything available. All right. So maybe we can take the next questions are the pizzas and drinks. Thank you, Willem. I actually have one, but I'll ask you later, which is why, if you said that the neural network that is more similar to the humans is the
Sigmoid.
but you said that the one that is mostly used with the computers is the
ReLU, yes.
But why? Why don't we use more the Sigmoid? Because of the computer?
Well, it doesn't work, and we
mean
talked
doesn't
about
work?
it's a really logical reason. Because if you look at the derivative of the sigmoid, it's 0 at almost all numbers below -4 it's 0, and it's almost 0 at all numbers above 4. So it only has a derivative at this small area. That means that the way to help for the right direction is really, really small. You only get a little bit help. And you can understand that if you have more and more layers, then you don't get any help anymore, because there is no derivative anymore. So then the network doesn't train, and you will see like it's dead. And the ReLU, every number bigger than 0 has a derivative, a very easy one, 1. So bam, then suddenly you get a lot more direction from the derivative. And this also has a name, the vanishing gradient problem, but it's already solved because now everybody is using value.
Okay.
Just a little question.
Okay, yeah.
Does the data science students make use of GPUs?
Well, that's a good one. So the NV link, they're gonna put it online on the cloud, but that most likely will be a paid service because nobody is offering it for free, because then the whole world doesn't. And then you can apply the GPU. So it will be, I think, in a few weeks it will be news that IBM has put GPU and NVLink power in the cloud, and then they're now busy with machines to make them ready for the cloud, for us to use. But there's a website, Ninix, N-I-N-X, and they offer 60 hours of free computation on this machine. And after 60 hours, you have to register. So then you have the chance to feel the power of this NV, and that's Ninix with X.
Sí, pero ¿quieres presentar la presentación desde aquí?
Presenta aquí, si no, no hay streaming.
Like other cloud services.
Like others, Google has the TPUs, and now the second generation can actually be used for training, so that's very good. And all right, well, so pizza talk about all the other topics. Thank you very much.
Bueno, pues muy buenas tardes a todos. Mi nombre es Raúl Marín, como comentaba antes Victoria. Y bueno, mi posición dentro de Horton Works es en el equipo de ingeniería preventa. Vale, entonces, bueno, cuando ha preguntado Victoria cuántos de vosotros habéis estado por aquí en anteriores ediciones, pues no habéis levantado mucho la mano. No sé si estuvisteis en las primeras en las que tuvimos nosotros, estuvimos comentando un poquito sobre Horton Works y qué somos actualmente en términos de producto y tecnología. Entonces voy a ir muy rápidamente y luego entro directamente en la parte de la demo. Vale, vamos a ver. La demo la voy a hacer con mi portátil porque voy a utilizar la infraestructura que tenemos en nuestra nube, necesito acceso VPN y bueno, vamos a ver cómo sienta el cambio. Bien, ¿cuántos de vosotros no conocía Horton Works hasta el momento? Vale, para alguno de vosotros es nuevo. De todos los que habéis levantado la mano, ¿conocéis Hadoop o es algo que da un poco de desconocimiento? Sí, Hadoop sí, vale.
Perdóname un minuto.
Sí.
Vamos a tener que parar porque es que han pedido las pizzas antes de tiempo.
Vale.
Entonces, pero a ver, debéis prometer que vamos a comer la pizza para que se enfríe, pero no os voy a hacer, ¿vale? Pero luego volvemos todos. Sí. Pues a ver, a las 8:20 lo volvemos a meter. Bueno, hay 4.
La cámara es donde las pizzas por aquí. Y está utilizando la webcam para hacer esto.
Sí.